All right, chemists. Excuse me. All right, chemists, let's get started. Hope to get through chapter 6 today. We'll see. If not, we'll finish the last bit up on Wednesday. It's just electron configurations, but we need to get to that point. And that means we need to solve the Schrodinger equation so we can figure out where we put electrons, especially for multi-electron systems. But first, let's consider hydrogen. And so just a reminder, that midterm 2 review session is tonight at 8 p.m. In this room and on Zoom. Just click on the page. Who's coming tonight? Yay. All right. So I'll see you then. All right. So we talked about the Schrodinger equation here. I'm joking. We will never solve it. You have to take physical chemistry 2. And then you'll actually solve it on paper. But the idea here, how this equation came to be, is we just introduced on Wednesday the idea of, gosh, my brain isn't working right now, the de Broglie wavelength, okay? And so the whole idea that, hey, if light can be a wave and a particle, then maybe particles such as electrons can also be waves. So we are considering electrons to be waves. So this is the Schrodinger wave function equation. It's treating electrons as a wave. We also talked about Heisenberg's uncertainty principle, the idea that electrons are really, really small. And so when we use the uncertainty principle, we see that the uncertainty in position is actually really large. And so that gives us the idea of atomic orbitals, the idea that we have s, p, d orbitals. These shapes are where we are most likely to find an electron. And that's a consequence of both de Broglie's work and Heisenberg's uncertainty principle. All right, so if we solve the Schrodinger equation, this is the solution you get. But what I want you to focus on are some of our quantum numbers come up here, our n value, our L value. And so the idea is how we can communicate to one another where to find an electron are with these quantum numbers. So there are 4 of them, and we'll go through what they mean in terms of the different orbitals we represent. So if you have taken a chemistry course before and recognize when I say s, p, d orbitals, those ideas are coming up. We're just going to kind of talk about it a little bit more deeply in relation to quantum numbers. And I want you to realize where these quantum numbers come from. They come from actually solving the Schrodinger equation, which comes up from the ideas of Heisenberg's uncertainty principle and the de Broglie wavelength. All right, so there's a large position uncertainty with electrons, so we need to talk about them in terms of probability. All right, so these shapes might look familiar to you. We have our s, p, d. We won't really talk about f orbitals, but I'll show them here anyway. But the idea is we are getting one step closer to actually placing electrons. How are these electrons arranged on atoms? We call this the electronic structure. So we get this kind of more detailed energy level diagram for a hydrogen atom. So this is the energy level diagram for the hydrogen atom. So notice that there are these little boxes here, all right, where we also have these n energy levels discussed. So we have n equals 1, n equals 2, n equals 3. These are the same n values when we talked about the Bohr model. See how there's a big jump between 1 and 2 and a smaller one between 2 and 3? But we're just bringing more detail here. We have these boxes that represent orbitals. So note how all of the orbitals within the same energy level, so like n equals 2 here, are all the same energy. See how like this one box is the same energy as these 3 boxes next to it. We call that term degenerate. We say that these orbitals are degenerate, meaning they have the same energy. If I wanted to place an electron in n equals 2, I could put it here, or I could put it here. There's no difference energetically where to put it, though a lot of folks will put that electron to the left, just because as humans we read left to right, or I guess as Americans we read left to right, so oftentimes we want to put that electron on the left here, but energetically it costs the same amount of energy to put that electron in any box because they're all the same energy. And that's the whole idea of this degenerate nature of these energy level diagrams. This is only specific for hydrogen. We'll see that it changes a little bit for other atoms. All right, so the big idea here, each of these boxes that are in this energy level diagram are represented by these orbital shapes that you may recognize. So how we can identify the size and shape and orientation is where our quantum numbers come into play. So for example, this is a 1s orbital, so it's going to look like this S shape. Here's a 2s orbital. It'll look like a sphere, but it'll just be a little bit larger. And then these 3 boxes, these are 3p orbitals. They will be represented by these different shapes, the dumbbell shape here. And we'll talk about why in the next sections. All right, so let's talk about the 4 different quantum numbers. So the first 3 are most important here. We have N, L, and M sub L. And so I already talked about here what these mean. So remember, these are solutions to the wave function of locating that electron. So our N quantum number typically relates to size of our atom, L, our shape, and M sub L, our orientation of different subshells of different L's. So I'll talk about how we get these different shapes. So we'll talk about the first one. We'll just go in order. That principal quantum number N. This is the same N as our Bohr model. All right, so as N increases, we know energy increases, but according to the Schrodinger equation, the size of the orbital also increases, or the size of the space where we find that electron increases. So we see that a 1s orbital is smaller than a 2s orbital. If we have an electron in a 2s orbital, it's going to be found in a larger area than a 1s orbital. All right, so that's our N energy level, our N quantum number, principal quantum number. So it only exists in integers, so 1, 2, 3, 4, etc. That's our first one. All right, so with our first quantum number, that brings us to our next quantum number. This is our subshell. So the possible L values we can play with depend on what energy level we are in. So notice if I go back up to this picture, see how there's only an s orbital in n equals 1, then we have s in a p subshell in n equals 2, and then we have s, p, and d. So the whole idea of s, p, and d, those relate to subshells or the shape of those orbitals. So the possible shapes we can have depend on the n value that we are in. So the rules are for, where do I have it? So for your possible n, depending on what n value you are in, your possible L values are all of the integers between 0 and n minus 1. So for example, if we have an n equals 4, if we're in an n equals 4 energy level, our possible L values we can have are 0, 1, 2, and 3, and that's it, right? Because it's our possible L values are all of the integers from 0 to n minus 1, right? So we can't have an L equals 4 here because n is 4. And so these numbers we'll see here soon are actually have meaning. Because these are the numbers that come from the Schrodinger equation. These numbers are actually the number of what we call angular nodes within the orbital shape. Or how I like to think of it is, these shapes S, P, D, all right? So all of those L values have specific letter designations, S, P, D, F, etc. So the idea here is that our L of 0, so 0, 1, 2, the L value is the number of angular nodes. That probably has no meaning to you. I like to think of these things as balloon animals. So if I had a balloon and I wanted to make a spherical shape, how many times would I have to twist the balloon to make a sphere? 0. All right, so what if I wanted to make a dumbbell shape? How many times do I twist the balloon? Once, yeah, and so then I have 2 lobes, right? And then what if I wanted to make this 4-lobed d orbital? How many times do I have to twist the balloon to get that butterfly shape? Twice. So I like to think of angular nodes as something like that. or sometimes they're called nodal planes. So the idea here is these L values have meaning, all right? They tell you the shape of the actual orbital itself. And of course, depending on the N value, those are the possible ones that we can have. All right, so do memorize these designations. So for example, if we had an electron that was N equals 3, L equals 1, we know that L of 1 is a p orbital, right, based upon this little chart here. So we would call that a 3p orbital. 3 indicating the N energy level, principal quantum number, and p by representing that L quantum number of 1. So let's name the subshell that possesses, name all of the subshells that can possess an N equals 5. So the idea in this question of N equals 5, let's name the possible L values we can have. If N equals 5, what kind of L values can we have? 0, 1, 2. Tell me when to stop. 3, 4. Okay, very good. All right. Okay, so we didn't quite answer the question yet. We have the possible L values, but let's name the subshells. So an L of 0 is what letter designation? S. So this corresponds to a 5s orbital. And then the same thing for L equals 1. We would have a 5p orbital, then 5d, then 5f for L equals 3, and then finally L equals 4. Now we just go in alphabetical order. It's 5g. We'll never go that far. We'll never go that far. Right? But that's how you would, put those ideas together. All right, let's look at this other one. Why is there no such thing as a 2D subshell? So if you look back on the previous slide of the energy levels of hydrogen, d orbitals start at N equals 3. So there's no such thing as a 2D orbital on that energy level diagram. You'll never find it. But let's kind of break it down to think about this. So that 2 means that N, our N quantum number is 2. Let's name the possible L values we can have if N equals 2. We can have 0 and 1. So now do you see why there can't be a 2D orbital? Because D is what L value? Is 2. So see how this is like a mismatch. We can't have an L of 2 because the only possible ones we can have are 0 and 1 if we're in an N equals 2. So that's why there's no, that would be a mismatch. There's no we can't put in an electron in a 2D orbital or 2D subshell. All right, so that's our L quantum number. So those are our different shapes. So this last quantum number of our first 3 is our orientation of these subshells. So basically the rules here we also call this the magnetic quantum number. It determines the orientation of our orbitals. The rule here is depending on what L value you're in, what subshell you're in, the possible orientations are all of the integers between negative L and positive L. How I like to think of this ML quantum number, it's how many boxes are in the energy level diagram for that subshell. So the idea here is, note how there's only one orientation of this s orbital. So if you look at any s orbital on an energy level diagram, you'll see that there's one box. If you look at any p subshell on an energy level diagram, how many boxes do you think there'll be? 3, yeah, because there's 3 different orientations. I have those there. D orbitals have how many different orientations? 5. So you'll see 5 boxes for d orbitals. So you'll see how this comes together, and this relates to the possible MLs that we can have. So if we follow this rule, the possible ML values are all the numbers between negative L and integers between negative L and positive L. If L is 0, ML can only be 0. So since there's only one combination, that means there's only one box. But then if we go to L equals 1, which is a p orbital, all right, so the first one's S, P, and then we'll do D. If we have an L of 1, ML can be negative 1, 0, and positive 1. So that's a total of 3 different orientations. So that's why there are 3 boxes. And then finally, of L equals 2, what are our possible ML values? Negative 2. Then -1, 0, +1, +2. So how many orientations did I just write? 5, yes. And so how many boxes are there? 5. That's how this all comes together, all right? Okay, so in general, what you'll see is depending on what L you are working with, the number of orbitals in that subshell or the number of boxes in that subshell. So a trick is when I say orbital, I mean a box, All right, the rule here is 2L plus 1. You'll see that trend here, that L of 0, there's 1 box. L of 1, there's 3 boxes. L of 2, there's 5 boxes. So how many orbitals will there be in a 2s subshell? 0? 1, yes, 1, because s is 0. And so if we plug that into this equation here, 2 times 0 is 0, but plus 1 is 1, right? The trick is here, all s orbitals will have 1 box, 1 orbital. So with that in mind, how many orbitals will a 3s subshell have? Also 1. So what you see here is the n value doesn't really matter here. It's just the L value that dictates how many orbitals there are in a subshell. All right, what about 2p? How many orbitals? How many boxes? 3, yes. What about a 7p? How many boxes? 3, yes, 3 orientations. And then finally, how many orbitals in a 5d subshell? 5, yes. So it's the D, it's the letter, okay, or the L value is what dictates the number of orbitals. All right, so we went through all I guess the most confusing 3 quantum numbers, and this will help us fill electrons and do electron configurations here in a little bit. So the last quantum number, because there's 4 of them, is related to electron spin. So this is related to us actually placing electrons into these boxes. So electron spin is m sub s quantum number. So the previous one with orientation was m sub L. This one is m sub s. So with electrons, one of their properties is spin, and so Pauli's exclusion principle, which we'll talk about in a little bit when we place electrons, says that no electron can have all same 4 quantum numbers. And so that kind of screws things up for us a little bit, because we want to be able to put 2 electrons in each box. 2 electrons can go in each orbital, but the only way we can do that is if their 4th quantum number is different. So this is why we put electron spin up and spin down in these boxes. So the spin allows us to put 2 electrons in each box, but only if they're spinning in opposite directions. So the possible ms values we can have are positive 1/2 or negative 1/2 to signify spin down. So this last quantum number just allows us to put 2 electrons in each box, but only if they're spinning in opposite directions. All right, so that's the last one. Okay, all right, so what's next here? All right, so let's put all of these ideas together, and let's write all of the possible quantum numbers for an n equals 3 shell. All right, so just remember the order. It's n, L, m sub L, and then m sub s. So if we are in n equals 3, what are the possible L values we can have? 0, 1, 2, stop. Okay, very good. All right, so now this is where it gets a little bit, we kind of have to break things down and look at the L's individually, because each of those L values represent a different shape. Each of those shapes have different orientations, so we need to figure out the possible m sub L's for each of those L's. So I like to approach them individually. So let's consider that L of 0 first. Let's ask ourselves, what are the possible m sub L's, the orientations of that s orbital? Just 0. So we see that there's only 1 orbital. So how many boxes? Just 1. Just 1. Okay, so the next one that we are going to consider is L equals 1. So what are our possible m sub L's? -1, 0, and +1. So how many boxes would that be in our orbital or energy level diagram? 3. Okay, very good. All right, because there's 3 different orientations, so 3 different boxes. And then finally, L equals 2. What are our possible m sub L's? -2 all the way to +2. All right, so how many boxes? 5. So 1, 2, 3, 4, 5. All right. So if the question asks how many orbitals are there in n equals 3, what would you say? 5? 9, yes. So 1 plus 3 plus 5 equals 9. There's 9 different orbitals, 9 different boxes within an n equals 3. See how we got that? Okay. So one step further here, what if the question said how many electrons can possess n equals 3? 18. How did you get 18? Why do we multiply by 2? 2 possible, yeah, so yes. So 2 possible spins for each box, right? We can put 2 electrons in each box. So 9 orbitals times 2 electrons per box, that equals 18 electrons. Very good. All right, so I think I have a little trick here for you. You can always try this yourself to see. You can change this question to any n value, and you can get all of the different ML values for the different L values, count the number of boxes. But there's a trick here. For any shell, there's n squared number of orbitals. And so if you want to then relate that to electrons, you can just multiply that n squared value by 2. So let's not even do any, let's not go through it, but if we did this question for n equals 5, right, n equals 5, how many orbitals are there in n equals 5? 25, yeah. So maybe at home you can try it, all right? You go through the same process. You do all the different L's, you get all the different M sub L's, you count how many boxes there are, and you should get 25 boxes. And then how many electrons would there be in n equals 5? 50, yeah, because 2 electrons per box. So try it at home. Okay, all right. So let's summarize these quantum numbers. Okay. So here's the summary, all right, of all the different values, size, shape, orientation, spin. Let's see which of these combinations are an allowed set of quantum numbers. So remember our rules. So we'll go through these one at a time and see, okay, is this a valid set of quantum numbers? Is it allowed given our rules? So let's do it one at a time. All right, so my process here is to kind of like think, go in order. So I like to think, okay, if n equals 3, what are the possible L's I can have if n equals 3? 0, 1, and 2. So I see that, okay, that's an allowed L that we can have. All right. How do we know, how is M sub L related to our electron? It's related to the L value. So given this L value, think to yourself, okay, what are the possible M sub L's we can have for this L value? It would be -1, 0, +1, because L equals 1 here. So -1, 0, +1, and we see, okay, that is an allowed M sub L, an allowed orientation. And then finally, is that spin allowed? Yes. All right. So let's, for fun, name that electron. What orbital is that electron in? 3p. Yes, it is. It's in a 3p orbital. It would look something like this. Cool. All right, let's go to the next one. Okay. So same idea, n equals 3. So that means we have the same possible L values. So is this L value allowed for n equals 3? Yes, it is. Okay, cool. All right. What about, so think about what possible M sub L values we can have for an electron that is L equals 0. Is this M sub L allowed? No, it's not. What is the allowed M sub L? It would have to be 0, yeah, because technically this combination, this is saying this is a 3s orbital. We can't have an orientation of -1. We can only have an orientation of 0. So this one is not allowed. A is allowed. All right, let's keep going. C. All right, so if n equals 2, our possible L's we can have are 0 and 1. So it looks like that L is allowed. All right, is that M sub L allowed for, what is this, a p orbital? Is L of 0 good for a p orbital? Yes, it is. What about that spin? No. 0 spin is not allowed. That would, in order for an electron to be in a box, it has to be spin up or spin down. So +1/2, all right, or -1/2, all right, okay. But for fun, given these first 2 or 3 quantum numbers, what If this was an allowed electron, what orbital would it be in? 2p? Yes, it would be in a 2p orbital. Okay. If the spin was correct. Okay, right. Yeah, this one's not allowed. All right, let's keep going. D. I'm not going to do this one for you. Just tell me, yes or no. Is it allowed? Yes? Are you sure? Do you bet your midterm 2 grade on it? Yes? Okay, yes, it is allowed. But let's check. N equals 3 are possible L values 0, 1, 2. So yes, L equals 2 is allowed. And so our possible M sub L values are -2 all the way to +2. So that M sub L of 0 is valid. And then finally a spin down electron, and that's fine. So let's take a second and draw what you think this electron would look like in terms of our boxes. How many boxes should I draw? 5, because it's a D subshell. So 1, 2, 3, 4, 5. Okay, so this is a 3D subshell. All right, and if I labeled each of these boxes with a number, -2, -1, 0, +1, +2, it doesn't necessarily have to be that way. I would have my electron spin down in that middle box, and that's perfectly okay. So that's what that would look like. Yeah? I guess we could, yeah. I guess we could, yeah. All right, let's keep going. All right, this last one, is that valid or not? Yes or no? No, what's wrong? The ML, yeah, how could we change it to make it correct? 0, okay. Oh, you guys are so good. Okay, we good? We good with this? All right, so, but remember, where do these numbers come from? We're in college now. Where do these numbers come from? Do you just have to memorize them? You know, they come from the Schrodinger equation, all right? So you guys are doing big things now, all right? That's coming from the Schrodinger equation, though we don't actually have to solve it. But I want you to recognize where it comes from. All right, so there we go. All right, so let's talk about now what these orbitals look like. Okay, so I've only been discussing the idea of, okay, we can find an electron in this space. I call that an orbital. I relate it to boxes, all right? Boxes in that energy level diagram. But these orbitals actually have shapes, so let's go a little bit closer into that idea, all right? So remember, this is the correct atom structure, right, of our hydrogen atom. We kind of went through that whole process all the way from Dalton to the plum pudding model to now. This is the correct representation of an atom. From the Schrodinger equation, we get the different orbitals, s, p, d. That's those L shape values. We have these pictures of what they look like. And the last idea here is, okay, can we graphically represent what these look like? So these graphs that I'm going to, show you in the next slide are actually the solution. If we graphically the Schrodinger equation, these are what the graphs look like. And this is how we can identify the probability of finding an electron. So basically these graphs are what give us these orbital shapes, our S, our P dumbbells, and our D butterflies that we have. So we're going to go into more detail here. So we oftentimes talk about the L quantum number, the angular quantum number, because it tells us our shape. All right, so that L quantum number 0, 1, 2, 3, our SPD, that talks about our shape. And I mentioned this before. That number 0, 1, 2, 3 is actually the number of angular nodes or the number of nodal planes in that shape. That's what the numbers mean, and that's the whole balloon animal thing that I talked about, the analogy. All right, to make an S orbital, how many times do you twist the balloon? 0. How do you make a dumbbell balloon? You have to twist it once, and that's how we get the shapes. That's where the numbers come from. So the number of angular nodes for a specific orbital shape is just the L quantum number, all right? So recall that each of these shapes are boxes on this energy level diagram for hydrogen. So here's our 1s orbital. That's the shape of finding an electron in 1s. Here's our 2s, again, one box, but 2p, 2p has 3 boxes because it's a p subshell. And then same idea here for 3s and 3p, and we see 3D has 5 different orientations. So always keep that in the back of your mind there. So let's go into detail of the different S, P, D subshell shapes that we have. So first we'll look at our S orbital and kind of break down the idea of the quantum numbers and what they represent. So S orbitals in general, we get S orbitals when our L quantum number is 0. And so based upon our definition in that previous slide, the number of angular nodes, the number of times you twist the balloon animal is 0. So that's why it's this spherical shape. That's why it's this spherical shape. So when we solve the Schrodinger equation, we get a L equals 0, 0 angular nodes. Basically what that equation is trying to tell you is that you can find the electron in this spherical density around the nucleus. And so oftentimes, so basically if at any time you were able to pinpoint an electron and you did that a million times, you would find that electron density would be, mostly close to the nucleus. Sometimes you would find it further away. The idea is that electron's zipping around all the time, but we can kind of locate, hey, that electron's in this space 90% of the time. And that's what the contour model shows, that like 90% of the time you will find that electron in this spherical volume. All right, that's why S orbitals, we show it as this spherical shape, because that's where we find the electron when L equals 0. All right, so we can also take a slice of this shape and think about it. Okay, if we call the nucleus this 0 point, we can also graphically show where the probability of finding that electron is. So this is called a radial probability distribution function. So the idea is, and I usually stand for this, what this graph is showing is that you will most likely find that electron, all right, at this distance from the nucleus. So around, around 1 angstrom away. So when the graph peak is high, it means that there's a high probability. Versus if you're like 5 angstroms away from the nucleus, you won't find an electron with that quantum number. So that is a N equals 1 S orbital. So this would be a 1s orbital. This next one is a 2s orbital, and this next one is a 3s orbital. So we see here as our N number increases, the most likely place that you will find that electron also increases, the distance increases. So note here for a 2s electron, see how the most probable distance is around 3 angstroms. It's further away from the nucleus. And then for a 3s electron, it's even further away. So that's the idea of finding, that's what this graph is trying to represent. Hey, this is the most likely place you will find that electron. So note, see how all of the graphs start at 0? See how all of them start at 0? Do you think you'll ever find an electron at a 0 distance from the nucleus? No, why? Electrons don't live in the nucleus. What lives in the nucleus? Protons and neutrons. Yeah, so all of these graphs will start at 0. All right, so those are the details for this radial probability function. Really what the y-axis is you're taking the wave function, the solution to the wave function, and squaring it. That's how you get probability. All right, so, I think, so some details about those graphs that I didn't mention before is, well, why do the graphs, like, we showed the 1s, the 2s, the 3s, why do they make this like roller coaster type thing? All right, you might have noticed I skipped over that. That's what this slide is for. So we talked about S orbitals in terms of their angular nodes. We already said, L equals 0. There's 0 angular nodes. Now the next kind of node that we can have is called a radial node. All right, so a radial node is, do I have the definition here, is the number of times the graph goes to 0 probability. All right, so the idea is for a S equals a 1s orbital, you'll only ever find that electron in that 1s orbital shape. So this graph actually has 0 radial nodes. So don't count the beginning or the end of the graph. So note that. But if we go to this next shape, so for a 2s orbital, what this graph is trying to tell you is that there's a small probability you'll find that 2s electron actually closer to the nucleus, kind of in the 1s region. But the majority of the time, you will find that electron in that 2s spherical region, right? But the idea is that you'll never find that electron between the these two orbitals. You'll never find that electron between 1s and 2s. And the whole idea here, I'm kind of going to go back to Bohr's, one of Bohr's postulates. I think it's the second one. I think it's the second one, right? The idea is that we need those rungs on that ladder, right, for that electron to be stable, that electron cannot exist between rungs of the ladder. And so that's what this is saying here as well, that we can't have that electron exist between different orbitals. So that's why this graph goes to 0. So this spot where it goes to 0 right there, that is one angular node. Right, remember, we don't count the ends of the graph. So how many, radial node. How many radial nodes does a 3s orbital have? 2, yes, because the graph goes to 0 twice. All right, so this has 2 radial nodes. So this is the equation. I would just memorize it. To calculate radial nodes is you take the orbital that it's describing. So in this case, let's look at a 3s orbital. The number of radial nodes in a 3s orbital is n minus l minus 1. So in 3s, what's your n value? 3. If it's 3s, what's your l value? 0. So wouldn't it be 3 minus 0 minus 1 equals 2 radial nodes? All right, so I would just say memorize that equation. All right? Okay, all right, so yeah, so we see here for a 1s orbital, you will find that electron, the most probable distance is around 1 or a half angstrom, but what you see about a 2s orbital is that most probable distance from the nucleus is closer to 3 angstroms. That as your n value increases, the probability of finding that electron is going to be further. The higher probability will be further from the nucleus. And I already mentioned this. All the graphs start at 0 because you can't have an electron inside the nucleus. Yeah? Why don't we just look at the next slide? Okay. You're so inquisitive. I'm slow. All right, yes, we'll do that here. All right, so for p orbitals, how many angular nodes in a p orbital? How do we get angular nodes? Memorize that equation too. Angular nodes equals the L value. It's in there somewhere. So remember, it's just the L value. So what's the number of angular nodes? 1. Yes, it's that simple. 1 angular node. Remember, it's how many times you have to twist the balloon animal to get that shape. All right. So what you see here is we have a way different shape for p orbitals, but those equations that I mentioned for radial and angular nodes, it still works here. All right. Okay, how many angular nodes are on a p orbital? We already said 1. So how many radial nodes does this shape have? How many radial nodes does that shape have? Okay, 0. Yes, it has 0. So if I told you that this is a p orbital, tell me what kind of p orbital it is. So this question is asking basically, okay, what p orbital has 0 radial nodes and is a p orbital, so therefore L equals 1. So basically we use that same equation, the number of radial nodes equals n minus L minus 0, or sorry, 1, minus 0, what am I talking about? Minus 1. So we just plug in what we know, okay? We already said that this graph has 0 radial nodes, so we need 0. I'm telling you that it's a p orbital, so it's n minus 1 minus 1. So then you just fill in the blanks. What is n here? 2. Yeah, n has to equal 2. So what kind of orbital makes this radial probability graph? A 2p, yes. So there it is. Except we did it a little bit backwards, all right, where I gave you the graph and you had to tell me what kind of orbital it is. But we could still get there the same way. If I asked you how many radial nodes does a 2p orbital have, you would do n, so 2, minus the L, so 2 minus 1 again, and you'll get 0 radial nodes. Right, so that's how we would approach that. Okay, for fun, how many radial nodes would a 5p orbital have? How many radial nodes would a 5p orbital have? 3? Let me check, I don't know. N, so 5 minus p, so that's 1, minus 1 equals 3, yes. So how many humps would the radial probability graph have? 3? So remember what 3 radial nodes mean. It means that the graph has to go to 0 3 times, but don't include the beginning and the end. So it would have to look like, so start off small. So 1, whoops, 1. So that's 1 radial node. 2, 3. Am I done? No, I'm not. I have to do one more. So there we go. That's what a 5p would look like, because you don't count the end and you don't count the beginning. So that's 3 radial nodes. Another way to think about it, so that's your 5p region, there's your 4p, there's your 3p, and then there's your 2p. P orbitals start at an n equals 2. There's no such thing as a 1p. So that's kind of how you would approach that. Yeah. Why do they level off at the end? Just because it's not as likely that you'll find those electrons further from the nucleus, like at that region. So it kind of tapers off. Yeah, but there is like a non-zero chance that you could find an electron that far away. It's just not that probable. Yeah, okay. All right, so there we go. So that's how you approach radial nodes and angular nodes. Okay, the last one here, d orbitals. Okay, how many angular nodes on a d orbital? Angular. 2, because L equals 2 here. All right. Okay, so here are the different shapes. And so you see that most of them look like butterflies, except our dz squared. So actually something I didn't mention before are the different orientations of these orbitals. So note the subscript in these shapes indicate how the orientation of these orbitals are on the XYZ axis. So the subscripts here, DYZ, is trying to tell you that butterfly is along the YZ plane. All right, where the lobes are between the actual axes. Or here, DXZ is trying to show that those the butterfly or the lobes are along the XZ plane within there. And same thing with XY. This one that looks a little bit different, it's x squared minus y squared. So this butterfly is along the XY plane, but the lobes are not between the axes. They're actually being bisected, like they're being skewered like a shish kebab along the axes. And then finally, the last one that looks weird is dz squared. And it almost looks like a p orbital, but it has a belt around it. So that's the idea, the distinction there, that dz squared has that belt. Let me quickly go back up to p orbitals, because I didn't mention it here. So remember, p orbitals have 3 different orientations, 3 different boxes. So showing the orientations of p orbitals are a little bit different and simpler, because there's only 3 orientations. You see that the lobes either align along the z-axis, the x-axis, or the y-axis. So we show that orientation by just the subscripts there, z, x, and y. Those ones are simpler, right? Because our p orbitals basically align along a line instead of d orbitals, which align along typically a plane, which is a little bit harder. All right, so let's do these questions. How many angular nodes would a 4d orbital possess? 2? I don't know. So n equals 4 here, so 4 minus a d orbital 2 is L equals 2, so 4 minus 2 minus 1, so 1. Oh, it says angular, oh, I'm sorry. Okay, so I'm gonna move that down here. Thank you, angular nodes. Wait, what's the answer? 2, yes, because L equals 2. You're right, very good. I jumped ahead. Okay, and so the next question says, let's draw the radial probability diagram for a 4d orbital. So that's where this next idea comes into play. It's ask yourself, how many radial nodes does a 4d orbital have? And that will allow us to draw the diagram. And so I already calculated here that the number of radial nodes is 1. So we just draw that graph with 1 radial node. All right, so does that have 1 radial node? No, that actually has 0 radial nodes. So I actually need 1 more hump. So there we go. So that's what that would look like for a 4d orbital. All right, so the last one here, f orbitals. So 7 different orientations. We'll never get this far, all right? I just wanted to show you the different orientations. My balloon animal analogy kind of breaks down here. So the number of angular nodes here will be not 2, 3. All right, 3. So we're just going in order. But we should still be able to determine angular nodes and radial nodes here. All right, so number of angular nodes in a 4f orbital would be 3. I will mention that I think in the online homework, sometimes it says nodal plane. A nodal plane is the same thing as an angular node, just so you know. They just sometimes switch between definitions or the things there. All right, so that's angular nodes or nodal planes for f orbitals. How many radial nodes would a 4f orbital have? So remember, it's n minus l minus 1. 1, come on. So this would be 4 minus 3 minus 1, so 0. So a 4f orbital would have 0 radial nodes. And then finally, a 5s orbital would have, 1 radial node. Because it's 5 minus 3 minus 1. All right, so that kind of summarizes the idea of our different orbitals. Remember that these are solutions to the Schrodinger equation. This is how we get those shapes. This is how we get the sizes. All right, okay. So now on to kind of the meat and potatoes of this chapter is electron configurations, all right? So we have the boxes. We should understand that orbitals are these boxes. They have shapes. They indicate, you know, how far away the electron is from the nucleus and what shape, you know, what volume area that you'll find that electron. So now the idea is let's put electrons in those boxes, in those orbitals. So remember, this is our energy level diagram for hydrogen. So there's a couple of rules of how we place electrons in these diagrams. So these are the 3 rules. So the first one is Aufbau's principle. So basically it just says when you place electrons in this diagram, you always place electrons in the lowest available spots first and build up. All right, so if we wanted to put an electron in for hydrogen, you would put it at the bottom first. Right, so like, for example, fill 1s before 2s. Don't fill 2s because that's like higher up. Those electrons will always go to the lowest energy spot first. The next one here, Pauli's exclusion principle, basically just says that 2 electrons cannot have the same 4 quantum numbers. Basically, in practice, it just means that if you need to put 2 electrons in a box in one orbital, one has to be spin up, one has to be spin down. So you can't have something that looks like this, right, where both are spin up. And then the last one, which is probably the most important here, is how to minimize energy when placing electrons in p or d orbitals. So the rule here for Hund's rule is you always want to maximize spin. Maximizing spin gives you the most stable arrangement of electrons. So for example, if I had these p orbitals and I wanted to place electrons, I want to maximize the spin, meaning I want to put them all the same spin in their own orbital first. I want to spread them out first. And that's basically what Hund's rule says. So for examples over here where we don't maximize spin, you don't want to place those 3 electrons like that. Right? That's actually higher, requires more energy to put electrons in that space. Because the idea here is you're trying to put 2 electrons in a small space when you don't have to. Because remember, electrons repel one another. So if you put those 2 electrons in the same box, they're going to repel one another. And so that's why this arrangement is less stable than this one. And so another way you can screw up Hund's rule would be something like this. Right? You want them all dancing in the same direction. That's the most energetically, the most favorable, the most stable arrangement energetically. You don't want to do that, right? Where that one electron spinning the opposite way, that requires a little extra energy to get that electron to spin the opposite way. Yeah. Yes, you can get them all to spin down. So analogous for the most stable arrangement would be to put them all spin down like this, but they all have to be in different boxes. They all have to be in different boxes. It doesn't matter. They're both correct. They're both correct, yeah. All right. Yes, because technically this does not violate anything if they're all spin down. The only reason that I put them spin up is because I'm human and I don't know, like I just do. And so the idea here also, I think I mentioned it before, if we had, you know, degenerate energy levels like this and I told you to put one electron in, a lot of folks will put electrons in this box just because we typically read left to right, but energetically it does not matter which box you put that first electron in, because all those boxes are degenerate, meaning that they're the same energy. So I could put that first electron in this box, this box, this box, or they could be spin down. That's okay too. We're not violating any rules when we do that. We just typically do it left to right because that's how we read. Okay, yeah. Yes, yes, yes. All atoms, everything in this world is always trying to find the most stable arrangement, always. Okay, so finally, electron configuration. So let's put electrons in these boxes. So how we do that? This is for hydrogen. You ask yourself, how many electrons does hydrogen have? 1. So then we place that 1 electron following all of those rules. So where do we put that first electron? In that 1s, so right there, that's it. So there's only 1, so that's good. So now we can write the electron configuration, which is obviously we can't write this on an exam, but we can, or like on online homework. But what we can do is use letters and numbers to represent where those electrons are. So the electron configuration is telling the reader exactly where you will find those electrons. So I will say, okay, you will find an electron in a 1s orbital. How many electrons are in that 1s orbital? Just 1. So the electron configuration for hydrogen is 1s superscript 1. If there were 2 electrons, we would put a 2 superscript. And that's it. All right, so that's only for hydrogen. So I mentioned before that the electron configuration for multi-electron atoms, see how the energy levels kind of are a little bit different now? And it's just because the Schrodinger equation, the solution is just a little bit different when there's more electrons on the atom. And so we see this splitting of energy of subshells, but that's all right. What we'll see here is that the periodic table tells us exactly what order to place electrons. But so this question says, okay, let's write the electron configuration for sodium. So we approach this the same way. How many electrons does sodium have? 11. So we place those 11 electrons following all the rules. So we start at the bottom. So 1, 2. Where do I put electrons next? 2s. So 3, 4, then 2p. So, but how do I place the electrons in 2p? Where does the next one go? Next box. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so did I place all the electrons? No, I need one more. Where does the last one go? 3s, there we go. And so the exact same thing. We, to write the electron configuration, you tell the reader exactly where you put electrons. So you start at the bottom, 1s, you put 2 electrons in the 1s orbital. You put 2 electrons in the 2s orbital. What comes next? 2p, 6, and then 3s1. All right. So in this example, it's pretty easy to see, oh yeah, you just fill lower boxes, you work your way up. But the problem is you won't be given this diagram, all right, on the exam. But thankfully, the periodic table tells you everything you need to know. All right, so the trick is that on the periodic table, the reason it's shaped this way is because of the S block, the P block, and the D block. And so what I want you to recognize is that your 1s start at hydrogen, your 2p's start at boron, and your 3d's start at scandium. So if you're given an element, all you need to do is locate it on the periodic table and kind of work your way from hydrogen all the way up to that element until you've placed the number of appropriate electrons in there. all right? Understanding where these different blocks start. If you in high school were told to memorize something that looked like this, did you do that? I don't know. It's like, I don't know, like, the chart, yeah, the thing that, and you memorize the order that they go in. Did you learn that? No? Okay, good, because that's stupid. You don't need to memorize it. You're always given a periodic table. You can get it from the periodic table. So let's try one here. So let's look at lithium. All right, so if you locate lithium on this weird periodic table, where will it be? It'll be like right here. It's right there, okay? So the idea here is you start at hydrogen and you work your way up. So you see you need to fill 2 electrons in your 1s and then 1 electron in your 2s to get up to lithium. Do note that hydrogen going over to helium, they're kind of split up. Both hydrogen to helium is filling your 1s subshell on the way to lithium. You can also write the shorthand version, which is where you start at a noble gas. It's like a checkpoint, all right? That you don't have to start at hydrogen. You can oftentimes start at a noble gas first, all right? So we can start at helium because that's represented by 1s squared, and then just write all the electrons that come after that, all right? So we'll finish this packet. How many are left? Like 5 slides are left, all right, on Wednesday. And then we'll do review after that. It's all that's left is electron configuration. So like I think at this point you can do this slide.